the largest number of particles that come into the Earth's atmosphere seem to be a microgram. This actually is not well established. It may be, in fact, a result of our observational techniques being particularly sensitive to microgram particles. So one of the objectives of this research is just to sort of flesh out this plot and get it right and see how much stuff is coming into the Earth. Okay, there are lots of other importances of meteor research, so I made this long, endless list. Of course, I come from the upper atmospheric community, and meteors are really important because they're sources of metals for the upper atmosphere. They modify the chemistry. They provide a dust source, which then can seed clouds, particularly high-altitude clouds. They create long-lived E-region ions, which affects nighttime conductivities. They're metal layers responsible for sporadic E. And I don't think I even put down the very important one that we can track them with LIDARs and other optical instruments. They give spectral lines you can look at for optical instruments. And then they're used to measure atmospheric winds and temperatures, not just by radars, but by LIDARs as well. They're really interesting plasma physics things. They're, billions of high-density plasmas created each day. They're highly energetic. There's enormous free energy as these things come in. And they drive plasma instabilities and turbulence. This is something I'm going to talk about today. They are important for solar system studies. There's a whole community out there that tries to figure out how much is out there, where it's coming from, what it's made of. And the Earth is effectively a giant particle detector. These particles come in at hypersonic velocities. They light up in the upper atmosphere, and you can read them off with your radar or your optical instrument. And there's a subgroup that's interested in particles coming from outside the solar system. That's a minuscule fraction of these particles may or may not be coming from the solar system. It's actually, there have been a few particles that really look like they must be, but that's a whole different topic. They're used for communication. You can actually bounce radio waves off the meteor trails and create meteor burst communication. They actually damage spacecraft. It's hard to know for sure what spacecraft they destroy versus other things destroying, but there have been all these objects that spacecraft, and this is an old slide, there are more recent ones than that, but there have been an awful lot of spacecraft that lose instruments or lose a fundamental system during a shower. So it's quite possible that they play a role. We typically don't know because you don't recover the spacecraft. But when you bring objects back from space, they're often very dinged up by these little particles. Okay, so I've been doing research now for 16 years at BU. I've had some great collaborators. My first two students got involved in meteor research. This is Lars Dierud and Sigrid Close. Sigrid's now doing this different kinds of meteor research in Stanford. Lars is doing lots of exciting stuff, less meteor stuff though. Anyway, so I did a search on ADS, and we've done 52 references in ADS and 27 papers. And basically we're trying, you get good at knowing a topic and you try and address any relevant question, and that's what we've done. What do you see? Why do you see it? Where are they coming for? What use are they? And lately, what can we do with the winds? Can we get winds off these meteors? So, okay, so here's some background science. So a particle comes into the atmosphere. It might be a microgram. Could be, 10 micrograms or 0.1 microgram. It comes in, and it's often moving 30, 40 kilometers a second, up to 72 kilometers a second if it's some piece of a comet or from the outer solar system, or as slow as a few tens of kilometers per second. Typically, the slower ones you don't see because they don't go through the process I'm about to describe. But a fast particle hits particles in the atmosphere, and actually, it's interesting, it predominantly gets hot. It doesn't seem to break apart much. It doesn't seem to, in the upper atmosphere, it just gets hot. And in the process, it gets hot enough to start sublimating. And it sublimates away gas, whatever it's made of. It could be silicates, magnesium, sodium, iron. Some things are easier to see with spectral instruments than others, so we tend to focus on the sodium because it has such brilliant spectral lines. It gets hot. Those hot atoms are typically neutral to start, but they're going 50 kilometers a second, perhaps. An iron atom going 50 kilometers per second has a keV in energy, and so that's many orders of magnitude more than you need to ionize that iron. And so the iron will get ionized, maybe even secondary ionization of the atmosphere itself, depending on how fast it's going. And so you generate a plasma, okay? And then at first you're going to have a very hot plasma, but it's in a highly collisional part of the atmosphere. It's going to expand out to a few mean free paths and cool rapidly, especially the ions. The electrons cool a little more slowly. And then we think what happens is, well, collisional diffusion will then begin once it's a few mean free paths. But then what we see with a big radar like Hikamarka or with particularly the Hikamarka Radio Observatory, which I'll talk about in a few minutes, we often see signals that look like this. You see, and this is actually, I went down, the first time I ever went down, and we did an experiment just to look at meteors. This is literally the first 5 seconds. So this is absolutely typical, not selected at all. It is the first 5 seconds. And the first 2 seconds were a little dull, but after that it got good. And you can see we got, in 5 seconds we got, 1, 2, 3, 4, 5, maybe 6 measurements. And then we got some very small ones, and then the bigger ones have these tails. And one of the things we didn't understand is what in the world was causing these tails. We think they're due to turbulence, and I'll talk a bit about why that's actually sort of a difficult thing to understand how that can happen, how you can get the appropriate turbulence. But let me first talk about where these particles are coming from, and how fast are they going, and how big are they. So for decades, people have been observing meteors using meteor radars. And the meteor radars are very simple radars. They're it's typically a couple of just simple wire lines, usually a couple of them so they can do interferometry. And they're not very expensive. And you can then figure out where the meteors are coming from by collecting years of data from radars all over the planet. And this is a composite observation, actually published the year I started doing research on meteors, so it's been useful. Just showing where you see them on an ecliptic coordinate system, where the particles are coming from. There's some names for them, the north apex, the south apex, and then there are some other sources. But a lot of them come from right there, and then there's these sources here. And I'm not going to explain all this, because otherwise I won't get to any other topics. But what was interesting is we started doing research. We had access to this huge radar. This is the Hikamarka Radio Observatory. It is this building fits 50 people working in it quite comfortably. This is 300 meters by 300 meters. 18,000 dipoles, each of which are about this big. I mean, this is a vast radar. It's one of the world's most sensitive radars, built at about the same time as the Arecibo Radio Observatory. It's an old radar at this point. However, of course, you can replace everything but the antennas, and have replaced everything but the antennas. It broadcasts at 50 megahertz, and it has a huge, what's called power aperture product, because it's such a vast radar. And it's also an interferometer, which is a hugely useful thing. So as a meteor comes through the field of view of the radar, you can see if the meteor is here or here or here or where it is in the beam. Because you can do interferometry. It's pretty easy. You can break this into 3 pieces or 8 pieces, however many pieces. Well, up to 16 pieces. They have 16 high-speed receivers. But you really only need 3 to tell where the meteor is in the beam. And you get a signal this is your typical signal from a meteor. You get what we call the head echo, which is this initial reflection. It really is as the meteoroid is giving off a gas, that gas is slamming into the neutrals and becoming a plasma. As it becomes a plasma, you're seeing the front edge of the signal, and that's the head echo. That's what this streak is here. And actually, the Doppler shift of that streak tends to be about 30, 40, 50 kilometers a second. So it tells you the speed of the meteoroid. Actually, you can see from the slope of the line what the speed is, too, coarsely, and then you can use the Doppler shift to refine it. You can even see them decelerating as they descend into the deeper parts of the atmosphere, and the atmosphere gets denser. So, because Doppler is really, really precise. So it's terrific. You can get a lot of information from that head. And then this is what we call the trail, which the second topic in my talk. We'll talk about this. This is the non-specular trail. There's often this gap between the two. Well, let me not get too distracted. What I want to point out is that you can get interferometry on the head, and you can figure out where meteoroids come from. You get signals that look like this. Here is, if you plot the beam pattern, sensitivity pattern of the Hikomarka Radio Observatory, that's this image on the left. This sort of to the first side lobe, the first nulls is about 4 kilometers by 4 kilometers. There are, of course, side lobes. Oops, sorry. There are side lobes. That's this. And based on the interferometry, you could tell where in the beam the meteoroid went. And you can see the signal strength tracks the pattern of the beam. And this is absolutely typical. You just sort of get it comes in a side lobe, goes boom, goes through the main lobe, you get a stronger signal, and then out. This is the SNR and dB on the left. And you can then get the velocity in kilometers per second. There's an aliasing issue. It's why it's a negative velocity, but that's easy to fix. And so we get a precise measurement of the velocity and a precise signal strength. And based on, and we get, if we get 2 to 4 a second, we have a lot of measurements. It's not hard to accumulate even 170,000 echoes. I just turn the radar on for a few nights, and 4 a second. You just do the math. This is represents a couple weeks, but and so we can make a chart of where they come from. And the interesting thing is this big radar sees a very different population distribution than the smaller radar saw. I mean, the question is, where are these other sources? We saw them distributed much more over the sky. And it turns out that we had a hypothesis, which is that this radar sees much smaller particles than the small radars. This gigantic, highly sensitive radar sees much smaller particles. And those smaller particles have a tendency to evaporate at a higher altitude. They just don't get so far into the atmosphere because they evaporate before they do. And so if we limit ourselves just to meteors from below 100 kilometers, then we actually get back to the original distribution, which was an interesting find. So it seems like we're seeing a whole different population when we look with this kind of radar, okay? And we're seeing much smaller particles. But we can see the larger particles that other techniques detect by seeing further. The other question, I shouldn't have flipped quite yet, is you couldn't even see shower particles. Nobody could. A lot of this research was triggered by the Leonids of 98 through 2001, which were so spectacular. And nobody could even identify shower particles. It turns out they were so buried in all the little tiny particles. You get 1 million shower, or not 1 million, but thousands of sporadic particles per shower particle. You couldn't find. But finally, by simply looking at particles that we can identify as big particles, because they make nice long traces and all that, you can figure, and because they get low into the atmosphere, you can find the showers. So that's sort of a summary. So we can see where things are coming. That's the astronomy of meteoroids that you can do. You can do quite a lot with these kinds of instruments. They're really nice that way. Okay, so that's one topic. And this is the topic that I really got in, that really drew me into the field. And I sort of spread out later into doing the astronomy of meteoroids. But what drew me into the field was, what the heck is causing this signal? It seemed like a concrete issue. When you see a meteor, and if it's coming across the radar is looking up like this. If the meteor, it's going to leave this path of plasma, right? And as it's forming, there's something to reflect off of. There's that front edge that's you're sending a signal up, you get a signal off the front edge as it's forming. But if you have a nice, smooth, sort of almost metallic, what we call specular reflector, the power from the radar should go off into space, and you should get essentially no signal back. And that's, in fact, if you look at any one altitude, like 98 kilometers, you see the head echo. It's basically a single pixel return. And then you see nothing after it. For quite a long time on plasma timescales, for many, many milliseconds. And then all of a sudden you see this sort of signal develop. And it's a question of why you would see a signal. Hikamarka is only sensitive to something that has a structure equal to half its wavelength. So Hikamarka emits 6-meter wavelength. It can really only see things that have some structure at 3 meters. 3 meters is not very long compared to the mean free path at 100 kilometers altitude. And so diffusion should wipe out that wavelength very quickly unless something were creating it, okay? And so that was the question of what creates it. Now, this region of the atmosphere where the meteors evolve and leave their plasma trails behind is called the E region, in part because it has a very odd physical system for plasma. It's a really weird plasma because in this region of the ionosphere, if you put an electric field across it, the ions respond by essentially traveling in the direction of the electric field, because, even though there's a strong magnetic field perpendicular to that, because they are collisionally demagnetized. They just essentially bounce from collision to collision. The electrons, on the other hand, are not collisionally demagnetized, so they E cross B drift with an occasional collision. And it's just because the ions are, well, if it's O2 plus, the ion is 50,000 times heavier than the electron, so the electron creates does a lot of gyrations per collision, whereas the ion would do a very slow gyration, and actually it does many collisions per gyration. And that from about 130, depending on your latitude, to 70 or 80 kilometers or so, you're in this regime where the electrons remain magnetized, but the ions are not. And it means that whenever you get a force, mainly electrical forces, on a plasma in this region, the ions go in one direction and the electrons go perpendicular to that across B. And so it leads to very odd physics. And that ultimately is what's responsible for these trails forming. And the way I've studied it, the way I tend to study almost everything at some point, is I do what I'm really good at. What I learned to do in graduate school is simulate plasma physics, particularly PIC codes, but also hybrid codes with some fluid components. And so when you have a hammer, everything looks like a nail. So in this case, the meteors look like a nail. In fact, when I first was going to, when Art first suggested I work on this project, it seemed like such an obvious thing because I was trying to simulate the gradient drift instability, which is done by very steep, long, slow, not steep, but slow, gradual gradients. But my simulator couldn't resolve the gradients. They were way too long. I just couldn't get big enough. The computer power wasn't high enough in the 1990s to do it. But a meteor has a very steep, short gradient, and I could do it. So it was really sort of the obvious thing that, in fact, I tried to simulate the gradient drift instability, for those of you aware of that. And I realized what I was really simulating was a meteor. So I was all set up for your question. And the way it worked is I often use the particle and cell. It's such a physical system. It's really nice. You just have a box, you put a grid over it, and you populate it with particles. And you give those particles an initial velocity, you give them an initial position, and then you figure out the charge density on the particle positions. Once you have the charge density, you use Gauss's law to figure out the electric field. And this is an electrostatic calculation, which is a reasonable approximation in this part of the ionosphere typically. Then once you have the new electric field, you just use the Lorentz force equation and you can accelerate the particles. Once you have then in this part, collisions are crucial, so you need to collide your particles with neutrals. That's sort of actually one of the things I had to invent for this, add to simulators, because it's not a typical thing, but it isn't that hard. Once you have a new velocity, you update the particle positions and repeat, and repeat, and repeat. And when I first started in the business, we did this on one computer. Now we do it on one computer that has hundreds of thousands of processors, like the Stampede supercomputer. And now we do it. PIC codes are actually really easy to parallelize. It turns out that's one of the nice things about them. And so the simulations I'll show you are, use 8,000 processors efficiently, and thousands by thousands by thousand grid sizes, and tens of billions of particles. And it's basically the same process, just divvied up across processors. And so we can get 10 years of CPU time in less than a day. So here's a simulation of a meteor that I think explains quite a bit of the physics and actually teaches us something new. So what we're talking about here is, this is the simplest model of what a meteor might have been. You assume that the meteoroid has already passed through. It's created a smooth column of plasma, right? And the column of plasma is probably densest at the middle and fades away with a Gaussian towards the outside. Since it is created through collisional processes, it's likely to be Gaussian in structure. Maybe, who knows, for sure. Actually, we're working on refining that, but that's the assumption for these simulations. And so, I'm going to simulate that to show, it's tricky to show three-dimensional. It's tricky to show three-dimensional plasmas. How do you show a three-dimensional translucent object, right, with no clear edges? So what I've done is there are three isocontours, meaning I picked three levels of plasma density, and the density is highest right in the middle of the column, and then I picked three levels. You can't even see there are three yet, but you'll see it in a moment. And then we did a cross-section where we just chose a density. The density, we put a plane that's the background neutral density. And then we let the simulator go and do its own thing, really. And just to see what happens. And we get quite an interesting result, as you'll see. So the first thing that happens is it starts diffusing out, as you'd expect. And then, but at the same time, it's very asymmetric. Oh, the magnetic field is, of course, this way. So it's not that way. It's along here. And you see, it sends out these wings along the magnetic field. And also, you see a little bit of wave structure develop along in the meteor, but not much. And so that was sort of our first simulation in 3D. And you can see you get sort of a diffusion, but it's mostly anisotropic. It diffuses faster along B, a little less fast perp to B. And the interesting thing at this point is these wings. Why does that happen? So we actually figured that out. What happens if you take the meteor and you just take a cross-section, and let's take the simplest possible geometry, and this will work for almost all meteors. But the simplest geometry is you have a meteor coming straight in. It's near the equator, so the magnetic field is this way. And then do a simple model where you assume the meteor has one density, and then outside the meteor, the background density. So it's called a water bag model. And so what you think happens is you're going to have different mobilities. I mean, first of all, along B, the electrons are highly mobile, okay? But the ions aren't so much because they're collisional and they're heavy. So the mobility is lower. Perpendicular to B, the electron mobility is dramatically reduced because they're magnetized. They're going to be stuck gyrating around the field lines. The ion mobility is pretty much the same as it is along B, okay? Which actually is often higher than the electron mobility, which means the ions escape a little bit outside the meteor this way, and the electrons start heading out along B, faster than the ions. And so you're going to get electric fields because quasi-neutrality, nature hates large electric fields. You can't really get the electrons away from the ions. So you get an electric field, and it's going to hold the ions in perp to B, and along B, it's actually a much smaller field, parallel to B, sorry. Much smaller field parallel to B, and it's going to hold the electrons in, right? Prevent them from going any faster than the ions along B, but it's going to keep the ions from going faster than the electrons perp to B. Well, the density of the plasma here is uniform, so it's just Poisson's equation, or actually even Laplace's equation, are going to tell you have to make this field nice and smooth and all mixed up. So, and actually it tells you that that electric field cannot stop at the edge of the meteor. It keeps going into the background plasma for many orders of magnitude times the size of the meteor plasma, depending on how dense the meteor plasma is. There's lots of little parameters. But basically, that electric field can't turn off quickly. It can't violate Poisson's equation. So you get this E perp that is driven by the plasma density gradients that goes often kilometers away from the meteor before it's substantially reduced in magnitude. And the electrons then flow along B to neutralize the ions. And what happens is that electric field that can be volts per meter or even higher, tens of volts per meter, probably some of the largest electric fields you're going to find in the ionosphere, basically takes the plasma. It's going to grab the ions. It's preventing the ions from getting away from the electrons here, but here it's going to take the ions and bunch them up. And that's what creates those wings that we saw in the simulation. And we actually thought those wings, we sort of had a hint that would happen from our calculations before we did the simulation, but we neglected them. We sort of said, it's negligible. And then we saw the simulations and said, oh my God, it's got to be important. Yes? Any background, or it's just the simplest possible system. I should have asked before I did it, but I'll do it now. And this is, anyway, we won't worry about this level of detail. So here's one with a background wind, which is the same as a background electric field, depending on your frame of reference. Does everybody understand what you're looking at here? I mean, to me, I've seen it so many dozens, hundreds of times. Actually, it took us forever. I mean, making 3D, making a picture like this that rotates and turns, and that took months of back and forth with ParaView until you're pulling your hair out. But anyway, is this clear what you're looking at? So here we're doing the exact same thing, but we run 100 meter per second wind that way, which is pretty strong wind, but not abnormal. It happens a lot in this region of the atmosphere. And then watch what happens. It's even more fun. So now you get waves on top of the wings. The waves extend into the wings, and you get all sorts of turbulence and wave development. It looks a lot like convection, right? Like neutral atmospheric convection, although the physics underlying it is actually sort of different. And the wind is blowing everything to one direct side, but at the same time, it really enhances this wave development, which ultimately turns into turbulence. And the simulator, of course, is great at exploring turbulence, right? That's what simulators are good at, the nonlinear physics. We can do the linear physics sometimes with pen and paper, but the nonlinear physics gets too hard. So we think this is why you see meteor trails and why they take a little time to develop, because you get these kinds of waves developing, and then there's basically the radar is looking at this thing from some arbitrary angle. Well, there's 3 meter structure at pretty much any arbitrary angle, particularly perp to B, to reflect off of. And so that explains the trails. And you can even see, you get some signal even if you're not looking at the actual trail, but you're actually looking at just the wings. Let's say the trail were in a null of the radar. We're way off the radar, and the wings extend. And these things can extend for many kilometers, and you should be able to see just this with the radar. And occasionally we see no head echo, and you just see what looks like a trail pop up. They tend not to be very strong because that means the whole thing is off in the side lobe. But So, I mean, the whole thing, the box size, I'm trying to remember, is something like 80 meters by 40, 80 this way by 40 by 40, I think. So the original, did you see the waves when they first started? They were pretty small, and then they actually cascade to longer wavelengths, which is sort of an inverse cascade from neutral turbulence, which is actually typical of this kind of turbulence, this E-region collisional turbulence. And so these are probably 8-meter waves, but there's certainly 3-meter structure in here because it's turbulent. You know, it's a spectrum, and would be sort of probably the dominant scale size. You know, but 3 meters, there's certainly 3-meter energy. I mean, you know, it's a broad spectral. When you look at the spectra, it's pretty broad. Yeah, you can do a linear analysis, and it has a range of growth wavelengths, and the peak of the growth tends to be at the gradient, at the length of the gradient scale length. No, of the meteor plasma. You have this very high density plasma, with a Gaussian edge, right? And so, so the gradient scale length is sort of it's a few mean free paths. Basically, it's about so the initial peak growth rate is a mean free path, order mean free path. So it's very small, and it depends on altitude, right? So if it happens at 100 kilometers, it's going to be longer than at 95 kilometers, or 93 down a scale height. So this actually was a paper that just came out in January. So it was nice, and you can see these movies in that GRL. You can now attach the movies to the HTML, and so it worked for me. I hope it works for other people who can see these. They're fun. They're fun movies. Okay, so that's the second topic. The third topic is something I stumbled into fairly recently because I was looking at all this complex turbulent physics, and I thought, well, getting winds off of these kind of radar echoes out of these trails would not work because you're looking at turbulence, you're looking at a mess. Turns out we get beautiful winds out of it. It just took it because I was suspicious that it would work at all. I didn't even test it for a while, and then I had an undergrad, and I said, hey, let's see if we can. What happens if you look at the phase relationship of the trail as it over time? And it turns out for long trails, the phases stay very coherent. You can actually watch the trail get blown across. So it actually turns out, even though you're looking at the turbulence within that trail, the trail as a whole, the turbulent structure is getting blown at the neutral wind speed. And so as a result, you can get winds with just essentially unprecedented, LiDAR level accuracies. I guess the LiDARs can do this too, but it's somewhat different configuration and somewhat different altitudes and resolutions. So I'm just going to, since I'm almost out of time, I'm just going to show sort of the latest winds we pulled out of some papers. And we're trying to do this as a regular monitoring program, but at the moment we just have sporadic data sets that we've collected. But basically, when you look at the wind speed, so here this plots wind speed. The color gives the wind speed, so everything from 0 to 160 meters per second, and versus altitude going from, we really don't get much above 107 kilometers down to 92 kilometers. And you can see we had a pretty consistent wind speed on this particular day, which was July 12th, 2005, of, sort of between, it's occasionally got up to 150 meters per second, but it was typically more like 100 meters per second and sometimes dropped down quite a bit. And down here, below 93 kilometers, it's a lot slower. But what's interesting is the shear, the whole winds, the whole atmosphere, the wind flows are changing directions rather dramatically. So this shows the angle of the wind flow, the east angle in degrees versus altitude. And you can see we go from, I cut off the color bar, I'm so sorry, but it's the same as this color bar. So we go from red to yellow. So they're turning, 180 to 0. So they really are wind shears in a very sharp layer. Down here, this one's interesting. This was another day in 2009, September 29th. We saw this blob of winds that at 100 kilometers or so, 100 to 105 kilometers, that sustain about 160 meters per second for over an hour and a half, maybe 2 hours. And, yes, they drop a lot below that, and there's a shear below it, but that's a really high velocity to sustain. And so from this data, you can get the wind shears out, and so we plot here altitude versus time from 3 data sets, and we get the wind shears. And the wind shears the units are meters per second per kilometer, which really you could convert into inverse seconds, but that wouldn't make any sense to me. But so it's the change in velocity in meters per second per kilometer, for those of you not familiar with it. And we get, often 50 meters per second per kilometer changes. I mean, they change incredibly rapidly. There's steep shears. This is actually an okay number because it's below the Richardson limit. But we sometimes see for extended periods of time, and in this 2007 data set, we saw, often greater than 80 meters per second per kilometer sustained wind shears, which are, maybe they're not far over the Richardson limit, but they're right at it, and they're staying at it for a long time. So it's an interesting technique. I know many of you are interested in winds in this audience. Oh, okay. Yeah, I pulled this from Han-Li Lu's paper. I mean, I'm a computational plasma physicist. What do I know about neutral turbulence limits? So it's if you have a wind shear, depending on the density, a neutral flow, and you have 2 gases flowing over them, at what point do you get a shear instability? And that's the limit of that's the threshold for the instability that starts. You get waves develops, and the waves will eventually turn into eddies, and that will just, once it's eddies, it basically spreads the wind shear over a much larger area. It mixes the winds. Below this limit, you can have 2 winds passing each other, and actually, you can get the strongest wind shears can be obtained sort of at this, just above the mesopause, in this mesopause area, in the bottom of the thermosphere, top of the mesosphere. That's my understanding is you can get you can get the strongest wind shears before you get turbulence. But we still get just huge. These winds are probably all sort of local gravity wave breaking energy. They're very localized. They're not the kinds of winds you see when you average over half a day or a day. You do lots of averaging. They're localized, high-resolution winds. And the nice thing about using the meteors is it's essentially unprecedented accuracy. And we just happen to have this gigantic radar sitting there all the time, and this is a good use for it, is just to collect this data. All right. We do, there's lots of other stuff you can do with this. We're working right now on trying to figure out what happens that instead of just having a column of plasma initially, we were trying to figure out how that process of collimating the plasma actually progresses, doing it a little more with more physics. There's a lot of nobody's dug into the physics of that for a long time, and the models are very simplistic, and we're trying to improve that. We try and see, can we, based on, you can get diffusion rates off the meteors, and can we actually say something about atmospheric temperatures and atmospheric about the atmosphere? Can we infer things from the atmosphere from the diffusion rates? And of course, we're also trying to set up a wind monitoring program at Hikamarka. So there's lots of other stuff you can do with the meteors. So that's my talk on the meteors. It's really given us, I think the last 16 years of research has given at least I've learned a lot about meteors. I hope other people have too. Yeah, it worked well for me. I got tenure, so that's a good thing. We've done a lot on meteor diffusion and waves and 3D simulations. We really basically understand these signals reasonably well now, whereas we really didn't before. We've found new things like the development of these wings that was not predicted before. It might actually be important for like nighttime ionospheric dynamics. You can make fairly deep troughs and in the ionosphere and ridges of enhanced plasma density that away from the meteors themselves for kilometers. And these meteors, there's millions a second, and particularly near dawn. And so structure up the whole ionosphere on a fairly small scale. We did a little estimate of how big that effect should be, and it's non-trivial at night. During the day, not so much. So what? Well, we can now better understand what we're seeing when we measure things with the radars, and presumably also, well, less so with optical measurements, but with radar observations. We, of course, can have this new wind technique, which has been fun. We have a better understanding of the fundamental physics, and so we've had some impact modeling meteors. So, thank you. See, 50 minutes, I'm trained.
Thank you, Meers. Your very high wind shears are reminiscent of the winds that Miguel Larsen measures from rocket campaigns, TMA trails. I'm wondering, are there other large aperture radars that could be brought to bear to do correlative studies using the meteor technique and the in situ observations to get at the underlying physics?
There are a number of other radars that could be. I mean, there's sort of anything mid-latitude to low latitude. It's hard to do it at high latitude because you have to look perpendicular to B, and so you're looking at a steep angle, and so you lose resolution. But Arecibo, if it could look perp to B, but it can't tilt much, can't do it really. There's a Chinese group that's actually put out a couple papers where they followed this technique, and they did it with 4 Yagis. They could only do it off the biggest meteors, and it was very coarse measurement, but it was 6 Yagis. 6 Yagis, which is a little different from Hikamarka with 18,000 dipoles. And so they, yes, it can be done. The EARS radar should be able to do it. Any sort of low latitude to mid latitude should be able to do it. If you can, well, yes, that would be especially nice. Yes.
So I'm just curious from a data perspective. You've got, millions of these meteor trails. How do you go into the radar data and pick them out? Is it some poor grad student that's staring at them, or do you have some tools be better than that?
Undergrads, actually.
Undergrad, okay.
These are great undergrad projects until their eyes fall out on the table, Koki Chow was the director of the Hikamarka Radio Observatory. He insisted all his engineers and analysts would spend an hour a day clicking through the meteors manually. We're trying to automate it, but it's hard because the electrojet gets in the way. The electrojet is a mess, and so it's hard to automate it. There's a lot of noise. The brain is a really sophisticated signal processing device.
I remember when the idea came up, or when we discussed this, it's because Susan Avery and her student Julie Chang had been measuring meteor winds, and they were getting vertical velocities of maybe tens of meters per second lasting for hours, and somehow this didn't seem really plausible. This is a Christmas Island, but it's similar latitude. And this is where we thought, well, maybe they're not actually measuring the bulk motion of the trail, but irregularities within the trail. Anyway, getting back to the point is...
It's great that you remember that, because I had forgotten what the original motivation of the topic from your point of view, because by the time I actually had an answer, I had forgotten that. I should have asked you again.
Well, this leads to the question of, your technique of measuring the wind shears and so on, you're actually tracing your kind of target tracking to get the horizontal motion. You're not Doppler shift of the
Yeah, the
the
Doppler
signal.
shifts seem to represent more the turbulence.
Yeah.
They're all over the place, and they're very spectrally broad.
So can you use this to get vertical winds?
I've tried. I've not succeeded. It's probably worth trying again, now that we even understand it. I tried it early on, and it's sort of, like I said, the spectra are so broad and messy, the Doppler spectra. So I haven't succeeded. It's worth another shot, I think.
So I think I'm certainly used to imagining these blobs of plasma as kind of an incoherent scatterer, where you have this range spread echo coming through. But you're actually looking at the phase from one range or altitude bin, and then tracking that to get the wind.
So what you do, you basically, right? You have two in one direction, right? You're just simply getting the phase difference of the reflector. It's not an incoherent scatter, it's a coherent scatter.
It is coherent.
You're looking at coherent. Now there's a fair amount of noise on it, so we can only do it with meteors at least 3 seconds long, because otherwise the noise tends to swamp it. You have to see a nice, you get a noisy signal with a line, and you draw a straight line through it. And then there's lots of caveats. You end up throwing away half the data just based on various criteria you set up.
Okay. I guess, yeah, all right. I just wanted to clarify that is, you approach that as a coherent scatterer.
Coherent, yeah. It's
okay.
Which really surprised me. I thought it would be more messy than that, but it turns out these are, compared to the, if you have a the beam pattern extends, many kilometers by many kilometers, and within that, this is tiny. So even though you have all this turbulence, it's all contained in a tiny volume, and it's expanding as it goes, but slowly, so.
So has the Hickenmarker data enabled you to get a better estimate of how much matter is falling into the upper atmosphere from meteors?
That's a crucial question, which we really need to work on, because there is this fundamental disagreement between what's seen and the amount that the models, the atmospheric modelers, see in the atmosphere. We see, the amount of stuff coming in seems to be far more than the amount that is actually seen by the LIDARs and the observations. So there is a disagreement. So that's an important question. And no, I haven't done it much. I've spent so much of my time focusing on the microphysics. But that's a proposal that almost writes itself. So.
I have a question. From the trail plot, you have the trail that what do you call it? The head echo, and then followed by other signals.
Right. Yeah.
And
I can go back
those,
to those.
I guess they're maybe reflect the diffusive or mixing nature of that place at that altitude. Can you use that to deduce, say, the turbulence, eddy diffusion, or more is reflect the instability of the plasma?
So it's 3-meter waves. It's 3-meter structure, and we don't think of that. That's near the mean free path of the neutral gas. So we don't think there's I don't think there's much structure, because on the Kolmogorov spectrum, that's in the part that's cut off, right, or very high loss, right. So it's the 3-meter structure is really a plasma phenomena. But the winds, presumably this stuff tells you something about the structure. And sometimes you see, of course we're just getting vertical cuts, right? It's as a function of time, so you can't see eddies or something, but there may be eddies rolling through here, right? And whether, the problem is you see these, like some days we get beautiful observations that are continuous, but then some days you have days where all of a sudden the observations cut off, and it's often because the electrojet turns on. It would be nice if Hickenmarker were just a few degrees, a few more degrees off of B, which actually may off of the magnetic equator of the Earth, then it would have less electrojet. And actually that's happening as the magnetic poles are drifting. So So, you know, if this radar were up like where Altair is, we would be able to get these kind of measurements nearly continuously because you wouldn't have electrojet getting in the way. And also, the meteors themselves are a little sporadic, right? The ones that have more than a big enough trail, sometimes they're just nonstop, and sometimes not so many, you know. And so when they're nonstop, you get a huge altitude range of observations. Sometimes the meteors, when there are fewer, then often the higher altitude and the lower altitude gets cut off. Usually right in the middle here at 96 kilometers, you almost always have enough meteors to get something. So yeah, so our data sets are always going to be a little spotty. You know, it's not, LiDAR is better that way, right?
Meers, you made what seemed like an offhanded comment right at the end where you said the meteor speeds are higher at dawn. Can you explain that?
So, you know, if I'm the sun, and this is the Earth, and, you know, if this is dawn, right? This is dusk. This is midnight, noon. 30 kilometers a second, the Earth is moving, right, around the sun. It's the windshield splatter effect. It's the bugs on the windshield. Meteors, you know, so at dusk we see far fewer. They have to catch up with the Earth 30 kilometers a second, you know, whereas otherwise you gain 30 kilometers a second. That was easy. I had that one.
The time evolution of that 3-meter structure is slow compared to the PRF and radar.
Yes, that would be right. Yeah, yeah. The radars. We actually, with Hikomarka, to do these measurements, that's one of the things we do. We turn the radar up to its pulse pattern at the fastest possible resolution. You know, because you want to really resolve to do meteor work, you want to really resolve the head echo and the trail at high time resolution. Hikomarka, you can run at sort of a microsecond resolution, maybe actually not so well. The whole radar starts ringing at microseconds, so you have to go sort of a few microseconds at best. But radars are fast. It's only because it's a 50-year-old radar that you have that limitation, because the antenna has, you know, it's not so perfectly aligned, and, you know, it's rusty in places. Yeah.
More questions? Let's thank Meers again.